Radioactivity, which is the spontaneous decay of the nucleus. Here's a very interesting chart. There are around 260 stable nuclear isotopes. Each one of these dots represents a different isotope of an element. So you can see here on the x-axis we plot Z, the atomic number, how many protons you have, and on this axis we plot N, which is the number of neutrons. And you can see this straight line right here. That's the line where the amount of protons equals the number of neutrons. You can see for lower mass isotopes you're pretty much on that straight line. You have the same amount of neutrons and protons. However, the larger the nucleus gets, this curve curves away from the Z equals N line, and you have more neutrons than protons to keep a stable nucleus. The way to view this, the red dots are the most stable nuclei. They last 10 to the 20th seconds, which is a huge number. The less stable nuclei are white and blue. They only have lifetimes of about 1 second. Now the reason you have more neutrons up here, as the nucleus gets bigger, and again, it doesn't get terribly bigger. Maybe it gets bigger by an order of 3 to 4 times. The nucleons are further apart, so the strong nuclear force, there might be some nucleons on either side of the nucleus that don't see each other. So what you have then is you have an excess of protons which are trying to split the nucleus apart due to the electromagnetic forces, and in that case they'll be less stable. So you keep adding neutrons and neutrons to keep a stable nucleus. Non-stable nuclei become stable nuclei by emitting radiation. This is called radioactivity, and it was first observed and studied by Henri Becquerel, Marie Curie, and Pierre Curie. There are 3 types. We have alpha particles, which are helium nuclei. So that's 2 protons and 2 neutrons come out together. That's a helium nucleus. We have beta particles, and this is a result of the weak nuclear force. There are 2 types. You can have a neutron converting into a proton, which will then emit an electron and an antineutrino. And again, the neutrinos are for college level, but at least this way you've heard the words. When a proton is converted into a neutron, it emits a positron, which is basically an anti-electron, or a positively charged electron, and a neutrino. These beta particles are the electrons that have been emitted and positrons. So when you hear beta decay, it's either a positron or an electron coming out of the nucleus. It is not one of the electrons that are circling the nucleus. It's coming out of the nucleus. And the 3rd type are gamma rays. These are very high energy, and since they're high energy, that means they have high frequency electromagnetic radiation, and this is released when an excited nucleus moves to a lower energy level. And when that happens, the energy has to go somewhere, so what it does, it's released in the form of a photon, a highly energetic photon. Radiation is deadly to the human body because as these alpha particles, beta particles, or gamma rays go through you and they strike the atoms in your body, they can rip electrons off, they can ionize them, they can do things to the nucleus, they can disrupt DNA. But fortunately, and this is an important part, they're not all as dangerous as each other. For example, an alpha particle gets stopped by a sheet of paper. So if you're wearing a shirt, the alpha particle will not get through to your body. Beta particles need a little more. They get stopped by a thin sheet of aluminum, so that would penetrate your skin. Gamma rays go right through you and deposit energy in your body and do tremendous damage. You need several meters of lead to stop gamma rays. So you might say, why do people worry about alpha particles and beta particles? It seems easy to protect yourself from them. The problem is if you ingest them. If there's alpha contamination somewhere around on dirt or whatever and it gets inside your body is not protected from the alpha particles on the inside. Your skin is very tough. The inside part of your body is not. So swallowing something that's emitting alpha particles would be very dangerous to you. On the previous couple slides, when we talked about nuclei emitting alpha particles or beta particles, you'll note that the proton number changes, which means when you change the amount of protons in a nucleus, you've changed to another element. Medieval alchemists which is not a real science, they attempted to change base metals such as lead into more valuable gold via chemical reactions. Well, of course they failed, because working with electrons does not change what the element is. It's still gold, it's still lead. However, nuclear reactions such as radioactive decay or fission and fusion, which we'll talk about later, can accomplish this transmutation of elements into other elements. So we can make gold from different elements. The problem is you can't do it with any economic value. It would cost you more money to make the gold than the gold is worth. But nuclear reactions do change elements from one element into another. Here we have the three types of decay again. We have alpha decay, we have beta decay, and we have gamma radiation. And there's a nomenclature for that. We'll start here with the nucleus, with an element X. X is the element name, A is the mass number, Z is the proton number. You emit a helium nucleus, which is represented by 2 protons and a mass of 4. That will leave you with the new element Y. Now notice, this has a mass 4 AMU less than this element over here. And if you add up the two A values, A minus 4 plus 4, you get A. And there you go. There's the A on that side. And the proton number here, you can see changed by 2. It went down 2. So very simply, the bottom numbers, the atomic numbers, have to add up on both sides to equal each other, and the atomic mass numbers, same thing. Beta decay is when the neutron converts into a proton and emits an electron. So here you have an electron, E minus, and here's this antineutrino. Don't worry about this again. Let's just cover these guys up. They're there to conserve momentum. We don't have to worry about it here. Now, you can see how when a nucleus loses an electron, its atomic number goes up by 1. Because over here, you have a -1 for the charge on the electron. -1 plus Z plus 1 is Z, and there you go, Z. The electron has no mass, so this element has the same mass as the original one. Now, and similarly for the positron emission, you're basically adding up the guys below the element, and they have to equal, and you have a +1 here. +1 plus Z minus 1 is Z, and there's Z. Gamma radiation, you keep the same elements. It just goes from an excited state to a less excited state. And the way you show the excited state is this little asterisk right here. Okay, so it starts with an excited nucleus. It goes back to the same nucleus plus a gamma ray. This leads to another conservation law. This is the conservation of nucleon number. This states that the total number of nucleons, A, remains constant for all nuclear reactions. Now, in the case of beta decay, a neutron can change into a proton, or vice versa. A proton can change into a neutron, but the total number of nucleons stays constant. Not the total number of protons or neutrons, but their sum will remain constant. Determine the missing isotope in the reaction below. We have polonium-212, and you have the missing isotope, and you have helium over here. Subtract the upper numbers to get the nucleon number, right? Because you have to have a conservation of nucleon number. 212 minus 4 is what? 208. Subtract the lower numbers to get the nuclear charge or atomic number. So it's 84 minus 2 is 82. So our element is 208 and 82. Use a periodic table to look up the element symbol for 82 protons. And you'll find, hopefully, that that's lead. So in standard format, we have lead 208 right there with 82 as the atomic number in the lower left corner. Determine the missing isotope in this beta minus decay reaction. We have beryllium here decaying into something plus an electron. Conservation of nucleon number, we need to have this number be the same on the right side. So you subtract 0 from 11 and you get 11. So you've got 11 nucleons there in this element. Then subtract the lower numbers, which is the conservation of charge, to get the nuclear charge and atomic number. So be careful with the signs. 4 minus a minus 1 gives you 5.
So we now have 11x5. Use a periodic table to look up the element symbol for 5 protons, and that is boron. So you write it as 11 boron 5, or boron 11. We now have sodium undergoing beta plus decay, and we need to find out who this is. The numbers on top, on the left side, have to equal the sum on the right side. So you do 22 minus 0, and you get 22. Same thing on the bottom for the charge. You have 11 minus 1, and that gives you 10. So on the right side, you have 10 plus 1. On the left side, 11. That's good. That's a conservation of charge. Go to the periodic table. Find out that 10 protons is neon. So you write it with the atomic mass in the upper left-hand corner and the atomic charge in the lower left-hand corner.